Welcome, everyone, to this fourth annual Pulse. I just want to make a few remarks, and then our director of Pulse is really going to kick off the show. But let me just say a few marks to get started. I'm Bill Sanders, Department Head of Electrical and Computer Engineering, and I have to say that it is my incredible honor to be able to welcome you here to this conference that is run by our students, for our students, and really celebrates the excellence of ECE. I think you know by now the 7 wonders of ECE, and it really shows all the things that people with ECE backgrounds can do. It's just an incredible festival. I want to give you a few facts about it to get started. This is the 4th year of Pulse, again, created by the ECE students. The attendance at Pulse has grown dramatically during those 4 years. 250 people came to the first Pulse. We're up to over 600 people registered for Pulse this year. Another first for this year is that Pulse has expanded from a weekend event to a week-long event, with events every night during the week, with speakers every night, and culminating, as you know, with a whole series of activities this Saturday. Dr. Jacobs, we're very honored to have here. In addition to him being the keynote for Pulse, I want to mention he's also one of our distinguished speakers for the ECE launch event. And you all know, and many of you were here for the opening and the dedication of the building last fall, and 2015 is the year of ECE launch. And clearly we're a department with a long legacy, but launch gives us the chance to look forward. And this year, we are going to have a series of very distinguished speakers, including Sir John Pendry, who will talk on metamaterials and invisibility. That's scheduled for March 10. Professor Lars Hansen, who's a Nobel Prize winner in economics, that will speak on April 22. Rafael D'Aria will join us in October for a talk on robotics. And we're going to end the launch year celebration with a 2-day event scheduled on November 5 and 6. So all of you as students are invited to all those events as well. I just want to close by thanking the entire Pulse team. And I can't read all the organizing members. It was a major event. But I particularly want to thank Ekta Shah, who invited Dr. Jacobs to come here for this keynote, and Ashwin Shivaraman, this year's director. And with that, I guess the keynote session of Pulse can begin.
ECE is just really cool because you can do so many things with it.
I've never been more thrilled to be ECE because I realized that, you know, you can bring actual change in this world with this degree.
And that's something that's really inspires me, excites me, making innovations.
Well, I've been to a couple of the ECE Pulses conferences in the past. And it's always been a really good opportunity.
The companies come and they're not really just pushing recruiting agendas. They're really here to talk about cutting-edge technologies and actually give some real meaty tech talks.
I'm looking forward to the tech talks.
I like the talks, like the people who you invite.
The tech talks.
I would say the guest speakers
From all across the board, especially since we're doing all the different disciplines of electrical engineering this year. I'm really excited to see how much diversity there is out there. So having this conference bring people out who are actually in the fields, I think is going to be really nice.
There's technology websites that'll tell you about things that are just coming out and why they're interesting, but then coming from these guys is completely different because they'll talk about it on a much more technical level, which all the electrical engineering students will understand, and that just makes it so much more interesting for us.
I'm really looking forward to the competitions they're going to have.
Competitions for sure this year.
The kind of like work students do, it's very inspiring at the U of I, and I think seeing the outcome of like what students come up with, I think that's something really exciting and innovating for me. So I want to see what that happens with it.
I just want to see like how, like given some problem, how students, can come up with different solutions to actually achieve that goal. So it was really good last year, but honestly, this year I'm raising my bar expectation.
I've heard nothing but good things about it every year.
And I think the team is doing a pretty awesome job as well. So I want to see what they come up with. So yeah, I'm really excited about that.
So yeah, I think that video could explain what Pulse really is better than I ever could. But just to throw it out there, Professor Sanders is giving you all the statistics, and you guys who have all been coming out to these events know why this is such a big deal and why everybody's such a positive. Gaining a lot of experience from all these talks, meeting all these new people, networking, and learning really about all the different fields in ECE. And that's why I call Pulse not just a conference about innovation, but overall a celebration of ECE. And we keep throwing out that word celebration. But I think this year, in its 4th year, it has definitely become the biggest celebration yet. With the week-long events of Pulse, but also we've included more industry partners. More companies are wanting to get involved and want to share their works to students. So this year, and in addition to the new building being here, I think this year has definitely proved to be the biggest celebration of Pulse yet, and really looking forward to see more with future years in this building. But this could not have been done without the ever supportive ECE department, all the people who work upstairs, around the clock in this building. Equally goes for the students, who are also around the clock here, late nights, just working away, the competitions, the talks, all of that could not have been done without them. And then lastly, all of you who have, at some point this week probably attended a talk, whichever interested you. That's why we did it throughout the whole week. You found something you found interesting, you want to learn more about it, and you got involved. And so I want to thank all of you for being here. But without further ado, I want to introduce a esteemed, world-changing, pioneering electrical engineer, which our everyday interactions with mobile technologies could not have been made possible without this man. He's taught at MIT, he's taught at UCSD, he co-founded Qualcomm, and retired as its chairman very recently in 2009. He is an IEEE Fellow, a recipient of the Alexander Graham Bell Medal, and a recipient of the U.S. Medal of Technology. But most important to all of us, he's accomplished, again, pioneering, ambitious, but for us, he's an inspiration and a treasured friend. So, ladies and gentlemen, let us welcome Dr. Irwin Jacobs.
Thank you. It's great to be here and be part of Pulse. It is really quite an undertaking. I've also had a wonderful day here so far, hearing from and meeting a number of students, hearing about what type of work is happening here, talking to a number of the faculty members, and finding a lot of it, in fact, overlaps a number of things that we've been busy with at Qualcomm. And so it just made it that much more interesting. And I must say we've been very lucky to benefit from having a number of students from here go and work at Qualcomm or be interns at Qualcomm. So we're very thankful to the whole institution. Been very positive. I thought I'd perhaps just give a little history of background and actually involvement then in the founding of 2 companies, Linkabit and Qualcomm, and some of the things that we were able to accomplish. And the fact that although started 2 companies, probably didn't do it in the ways that are normally suggested, that when you take a course in entrepreneurship, you probably will not find that this is the advised way to get started, but in fact, it's worked out pretty well. My first company is called Abed, and obviously a funny name, but linking bits together. It resulted from my moving to San Diego, and let me just give a little bit of history of that. I was an undergraduate at Cornell, did my graduate work at MIT, stayed on as a faculty member at MIT for 7 years, gave a course in communication theory, advanced, how do you use information theory in what would become a digital world, but at that time that wasn't quite recognized, and was lucky enough with another faculty member to be able to write a textbook, perhaps the first textbook on book on digital communications, I think, and just some other work that I had done, there were many requests for consulting. And typically, a faculty member might consult a day a week. In fact, I think it's a very useful thing to do because you find out what the real world problems might be, and you can always direct research one way or another, and it helps to have something in mind that can, in fact, be practical. But I had many more requests for consulting than I could handle on a day a week. I mentioned that to two friends who were faculty members at UCLA. They said, let's start a company and share the consulting. And so that's how Linkabit actually started. Did not have a plan in mind, knew we didn't want to consult continually, but the area was growing, and so we found we better hire a few full-time people. And then in 1971-72 academic year, I realized that it needed some further organization, took a year's leave from the university to get it organized, found that was fun, and decided then to retire from my academic career and run a business. The choice of going into business, how do you rationalize that? Because for 13 years I've been a faculty member. And so one of my rationalizations was that for 13 years I've been telling students that the theory is very important, get a very good theoretical basis, and many would say, why bother? How's that ever going to be practical? And so one reason for starting a company was to be able to show that a lot of this theory was indeed very practical. Well, we started again as a consulting company, but very quickly we began to get some contracts. And one of the contracts is shown on the left of that. It was to the ARPANET, which was the beginning of the packet switch networks, was just beginning operation around the US, actually connecting universities and a few companies. And we won a contract to extend the ARPANET over to Europe by using a satellite connection. I went over to Europe to visit some of the telephone companies, the so-called PTTs, to see if we could get support over in Europe. And my memory is that we always had a very nice lunch and then were escorted to the door because who would ever be interested in packet switching? Luckily, we did find a couple of universities to work with and a few government laboratories, and so the project did go ahead. In fact, shortly after it was completed, the Internet protocol was also completed, and so we were able to use actually the ARPANET, the satellite net, SatNet over to Europe, and a packet radio network, connect those two using the Internet protocols. It was actually the first demonstration of the use of the Internet protocol, which of course at that time you didn't think very much about, so that's another something of interest. But 20 years later, the Computer History Museum said, hey, that was something we ought to celebrate as an event, the 20th anniversary, and so we did have a bit of a celebration and a party. Our approach to life was always to look for better ways of doing things, not just something that would be a little bit better, but is there something that we could do that was very innovative? And so in the upper middle, it's a satellite terminal. It was originally built for the Air Force, designed, built for the Air Force. And we had won a contract to provide such a terminal that would work actually with a few different satellite systems. And the usual approach at that time, this again was back in the mid-70s, was to build everything out of hardware. And we came up with the idea that perhaps we could use a processor. There were no single-chip microprocessors at the time, but there were ALUs, arithmetic logic units, register chips, memory chips. We could perhaps use those to build a processor and do most of the function in the processor. Which processor to use? Well, we decided that to keep the hardware down and the memory requirements down, we'd use a 32 instruction set multi-stack machine. And it was actually the first RISC processor, reduced instruction set processor. I don't think that concept had come out of the universities till about 8 or 10 years later. But that was the direction that we decided to follow. We came up with the design and took it through a prototype. And then the question was to go into production. And we were competing with a major aerospace company. And they had taken the more traditional approach of building everything out of hardware. And so we had to get agreement from the Air Force to get a little bit more funding and the right to prepare for production. And I went up to visit a general up in Los Angeles at the Space Command, and he had been briefed on what we had been up to, et cetera. And he started out by saying that I'm a project engineer on this program. It's very important to national security. I have a very large company. I've worked with them before. They may not be able to accomplish everything to the spec, but I know that if I give them the job, we'll get something about right. And so I thought that was the end of the possibility of our being able to go ahead. And he paused, and then he said, but as a taxpayer, I'm going to give you the support to go ahead and compete. And we did go ahead and compete and did win the contract. In fact, not too long after that, I ran into a project engineer competing for follow-on some business, and from the other company. And one of the tricks here, it had some frequency hopping, some spread spectrum aspects to it. You had to generate an encryption sequence to select each frequency. That depended on a code that you would enter and then time of day. So every 5 milliseconds you get another code word. And there was a requirement on that to be able to enter a new time of day and generate the first crypto word 3 seconds later. Well, the design for this had been given as, again, several pages, actually a book full, of hardware. The other company had built the hardware just according to that design, and they could never meet the 3 seconds because no matter how fast, using echo logic as it was called at the time, meta-coupled logic, you could never make things run fast enough to do it in 3 seconds. We come up with a way of doing it on software. Actually, it often pays to fly on airplanes where people aren't bothering you, and the idea for perhaps to do this came up on one airplane flight. And we were able to do it in software. So this project engineer came up to me one day and said, I understand you're doing that in software. And I said, yes. And he said, and that you can meet the 3 second requirement. And I said, yes, we can. He looked at me and said, you're a liar. So that actually prepared me for some as I'll touch on a little later, some future incidents where when you try to do something a bit differently, then you're always going to run into people that are skeptical, that say that can't work or you shouldn't bother with it or whatever, and that it's still important to pursue it. and sometimes you get a little bit of abuse in doing that. So that was another project we actually went into production on, and those units, as far as I know, are still running because you can upgrade the firmware to have them work with the different satellite systems as they get updated. We also worked on satellite communications using small terminals, and that one was interesting because we had Schlumberger that was doing oil drilling put out a contract request for equipment that they could use in an oil field that people with no experience in communications, and particularly setting up a satellite terminal, could do so, take that data, send it back to their customer, who would then decide whether to keep drilling in that hole or go on to the next one. In any case, we came up with a small terminal to do that, got the FCC to approve having terminals that didn't have a fixed location ahead of time. Until then, all the licensing had been done depending on the location of the antenna. And we then took that idea and made a commercial version. The first company to make use of it commercially was Walmart, to connect up all their stores and warehouses, and second was 7-Eleven. Anyway, it became a key part of business strategies. And finally, another program that came up, and again, these are not projects that we had in mind ahead of time. So again, one of the things I always advise is to be always open to a new idea, to a new thought, a new way of doing things, and be prepared to move quickly if some good idea does spring up. And this was a scrambling system for HBO to scramble their satellite to home TV signals. This was before we had all the broad use of satellite to home television and or internet delivered. And originally, all they wanted to do was scramble the signal from the satellite to a cable head, and then they distribute it by cable. And so we designed a professional unit, something that could be handled by a trained person and was a little bit more expensive, et cetera. And then I had my first exposure to politics, in a sense, that a group of backyard dish owners went to the Congress and said, we've been receiving these signals, we have a big investment in our backyard equipment, you can't simply let HBO cut that off, we're willing to pay something for it, but you have to give us a way of doing that. And so we had to suddenly design a small home unit, something that was low cost, reliable, didn't take any professional person to maintain it, et cetera, rather than the more professional unit. And how do you go about doing that? Well, obviously you needed to have integrated circuits. The problem was, back at that time, there was no automated design for ICs. And so luckily, there were a few universities that have been working on it. So I had one of our engineers, thinking that this was something that could be useful in the future, go and spend some time at Caltech. We went to University of Washington, went to MIT, and got various software. Had brought it back. We were getting ready to do some homework problems on that software and add something to it when we had to develop 3 chips for this descrambler. Luckily, we proceeded ahead. All 3 chips worked the first time. It turned into a huge and very profitable business. We actually set up a factory in Puerto Rico to manufacture them. Why Puerto Rico? Again, you have to look at all the various factors. At that time, if you manufacture in Puerto Rico, all value added in Puerto Rico was tax-free in the US when you sold it. And so, again, just a tremendous advantage. And so those were the kind of things that we did at Abed. Again, we didn't have any of these ideas ahead of time. We never went out for venture capital, but we kind of built one upon the other. So we bootstrapped our way up and managed to get various products done. However, we had also used stock options as a way of providing ownership to all the employees, and some point the liquidity of those options became important, so you either had to go public or sell the company or merge with another company. We decided at that point to merge with a company that was in the component business called Maycom. We did that, stayed on for 5 years. Things always happen when you do that kind of operation. and so I ended up retiring. Managed to stay retired for 3 months, and decided that that wasn't really very much fun. And there was a number of people from Linkabit that said, oh, we ought to do this over again. And so we decided on July 1st of '85 to start Qualcomm. But I cautioned everybody that Linkabit had grown 50 or 60% every year, was always profitable. That with Qualcomm, you know, that was, you can't expect to do that twice. And so maybe we'd get to 100 people, but the main thing was that we'd have interesting things to do and good people to work with. And so that was the motivation for starting Qualcomm again. Didn't have a business plan, didn't have a product in mind. Knew that digital would be of interest and wireless would be of interest. And so we did get started. Actually came up with several ideas in the first perhaps 5 or 6 months of the company that pretty much kept us busy ever since. One of those was CDMA, and I'll come back to code division multiple access for the wireless industry. Came up with that on a ride back from a consulting job in Los Angeles that had to do with mobile satellite communications. Realized that perhaps the standard TDMA and F time division, frequency division multiple access was not the right way to go, that code division might offer some advantages. We didn't have the money at the time to carry that any further forward. We had already started on a program to provide a satellite terminal for the trucking industry so that they could use satellites to have two-way communication with the trucks and have position location. By the way, position location is straightforward these days. We have GPS, it's all on your phones. But at the time, there was no GPS. And it was just beginning to get into experimental use. And we basically designed our own GPS system by using a small signal on a second satellite, combined with this communication signal on the first satellite, being able to measure the flight time delay between the two, figure out what altitude the truck was at from roughly its location, and get a fairly good location determination. So we built our own, in some sense, GPS. These were also spread spectrum signals, and so we had the megahertz bandwidth that GPS signals use these days. Always problems. This one had an issue with how do you design an antenna that you put on a truck, very inexpensive, in this case $50 or $60, would track the satellite, have about 19 dB of gain, and be reliable on a device that's shaking like crazy. The trucks are very rough riding. And again, and luckily this actually went back to some EM theory courses and antenna courses that I had as an undergraduate at Cornell. I realized that rather than trying to make an RF junction, you could simply stick a probe up, have a device rotate around it that looked like a waveguide, that was a waveguide, that then had a cone on the end of it to actually send out the signal. You could build something very inexpensively that would do the job, and indeed that did work out. And so we launched this Omnitrax. Took a couple of years, of course, and near bankruptcy a few times, to get the R&D completed, get FCC approval, get the marketing and sales done, and get our first sale. That first sale then gave us the funding and the cash flow to go back and let's take a look at CDMA again. And so we decided to go and see if in fact CDMA still looked promising, but not for satellite use, for the cell phone use. And cell phones, this was in the end of 1988. The first generation of cell phones was out there, which was based on analog transmission, FM radio, and had indeed been growing significantly. There's always a story that AT&T gave a consulting company in Boston a contract in about '85 or so to, because the cell phone technology was invented at Bell Labs, whether AT&T should go into that business. And the consultants came back and said, well, maybe in 2000 there would be 1 million users. And so it was off by 2 orders of magnitude. And so they decided not to go into the business. But by this late '88, it was clear that it was growing rapidly, and the industry realized that analog was not the right solution. You have to go digital. How do you go digital? Either with FDMA or TDMA. Every lab around the world had looked at CDMA, code division, and decided either it wasn't going to work, too many problems of various kinds, and had given up on it. There was a vote in January of '89 to decide whether to go with TDMA or FDMA here in the US. The vote was in favor of TDMA, but it was very bitter. Companies on both sides fighting like crazy. We came along about 2 months later saying, okay, we've looked at CDMA enough, we think it's promising. You should look at this. And of course, nobody wanted to hear anything about that after the fight that had just been completed. And so we had to go a little bit further. We did convince the industry to set up a meeting with about this number of people, I think in Chicago, not too far from here by the airport, that we could make a slide presentation how we had solved the problems with CDMA, and that we thought we had, and that that was something that should be considered. I thought there was about a 50% chance that, as I was making a presentation, that somebody was going to raise their hand and said, there's the point you missed, this is why it's not going to work. But luckily nobody did come up with that point. On the other hand, nobody believed it either, because seeing a set of slides is not too convincing. And so we had to go ahead and build a demo system, which you see here, which we did with a couple of base stations and a mobile radio, which took a van to drive it around in San Diego. And we invited people back in November to come and see this demonstration. By the way, as any of you that have given demonstrations, either to a faculty or fellow students or in business, no, they never go smoothly. There's always drama. And so with this particular case, I was just getting ready to tell people to break into groups to go, some ride with the car, some go to the lab, so you could hear both sides of the call. And there was an engineer waving from the back of the room to keep speaking. And there are many advantages to being a university professor, but one of them is you can always talk for another 50 minutes. And that's about what it took, about another 50 minutes, and luckily at that point did get a hand wave that said it was okay to send everybody out. And what had happened, it wasn't even our equipment. I mentioned GPS. We were using the experimental GPS satellite to provide a time and frequency reference for our base stations. One had come over the horizon with a bug, threw us off, took a while to figure that was the problem, resync, and then send everybody out. If it took another half an hour, I suspect there wouldn't have been a Qualcomm, but luckily that didn't happen. And so we were able to demonstrate that. But then the problem was, how do you go ahead and go from a van-sized phone to a phone that's commercial size? And obviously to do that, you have to develop chips. And to develop chips, you have to have a lot of dollars. And so the question was, how do you get those dollars on something that most people still didn't believe in? When we talk about innovation, you innovate often on the product you're trying to sell, but you can innovate in many ways. And another area open for innovation is business plan. And so we went and spoke to carriers. They were interested in the possibility of CDMA because it had the promise, we said, of giving them at least 10 to 20 times the capacity, the number of subscribers that you get on an antenna in a given amount of frequency spectrum that you could get with analog. Whereas the TDMA that everybody was moving towards could only give at best a factor of 3. So there was a strong economic advantage, because spectrum is limited, to going with something that's more spectrally efficient. We convinced enough carriers, operators, to go ahead and talk to their manufacturers that they should work with us to at least give this a try, we came up with an idea of a licensing plan that would give us some funding up front for signing a license, and then should this ever become commercial, it would pay us a royalty per unit sold. And most people were most concerned about the money up front because nobody really thought it would ever become practical. And so that way we got enough manufacturers to sign up to give us the funding to proceed ahead to develop the chips. That all did work out. We carried that through a ability to demonstrate that we had a phone that would work. That then allowed us to go through a standards process. Got through the standards process. The first system went commercial in Hong Kong in October, November of 95. So it was 7 years from the time we began to look at CDMA seriously to actually having the first commercial system. And there was a lot of controversy. Why Hong Kong? Because there were a lot of people carrying phones around because they didn't have offices, and the spectrum was terribly congested. CDMA was a way to overcome the congestion. The next two systems were in South Korea. The interesting thing was that we, at that time, could not convince anybody to build a commercial handset. We had to make them to demonstrate that CDMA did work, but nobody else had gone that path. And so all the handsets that we used in Hong Kong were manufactured in San Diego and shipped to Hong Kong. All the handsets that we used for the first two operators in South Korea, manufactured in San Diego, shipped to South Korea. The world has changed since then. And in fact, the way that we had managed to convince South Korea to become interested in CDMA, and we went to, I spent time in many countries, but the argument there was that South Korea was already trying to compete in high-tech manufacturing. The main competitor was Japan. However, and the only way they could compete typically, since they were always a year or two later, was on price, which is not the best way to compete. And so we went with the argument that here's CDMA, Japan has decided to go with TDMA. If CDMA should work, you'll have a leg up on Japan, you'll be there first, and you can then build a business. And they decided to take that risk and go that way. Two companies that were among the first to work with us on that had essentially no cellular business at the time was Samsung and LG. And so indeed that whole process did work out very, very well. In any case, we started to come back to the US, and again, everybody's very skeptical. So this is a piece from a front page Wall Street Journal article talking about Jacobs pattern that I was selling companies on something that had a strong chance of not working, would cost everybody billions of dollars, and then finish with a quotation from a professor at Stanford who said that we had problems we didn't know how to solve, basically. There was another professor at Stanford that was a little stronger. He said that we violated the laws of physics. Nowadays, I do give talks at Stanford, and whenever I do, I point out that CDMA now works everywhere in the world, except within a 5-mile radius of Stanford. So, and it was interesting. One of the concerns that the professor who actually objected to CDMA there was that CDMA was too complicated, and that therefore expensive. And he was basing that essentially on, the chip you could build that day. But whenever you're doing anything, you always have to look ahead, not what's available today, but what's going to be available when you're out there trying to sell that product. And so Moore's law was quite crucial. To build those first handsets, commercial handsets, it took 3 chips just to do the second generation of CDMA. Now, one chip does a lot that I'll come and touch on very quickly, but the cellular, this religious battle I mentioned in the previous slide, did continue through the entire time of second generation, which was mostly focused on voice. Then about the turn of the century, the industry recognized that they needed to also provide mobile data, internet access in particular, and as well as voice, and that they needed a technology to do that, and finally everybody decided that yes, CDMA is the way to go. So all third generation of the cellular is based on one of three flavors of CDMA. And so the religious wars finally ended with the third generation. And so then we were able to focus on the devices you carry with you. How do you get more and more, knowing that we were going to have very high data rate capability available to the phone, how do you get a lot of computing power in that phone? And so one of the things that always has struck me, and I think we all recognize it, that the computing power, given Moore's law, that you can double the number of transistors every roughly 1.5 to 2 years on the piece of silicon, that over the years, not only that, but you could reduce the power per transistor and indeed even reduce the cost. The last couple of generations, the cost is not going down, but we're still getting the greater density. In any case, it took, again, the 3 chips to do it for the first phones, and now we have chips that provide all these various capabilities. So handle second generation, third generation, now the fourth generation, which is built based on OFDMA, offset frequency division multiple access, and so it has to handle all of those capabilities, has to provide a very powerful computing capability, has to have very strong digital signal processors to do the voice and video compression, has to provide the graphics, has to receive position location from now 3 different and soon 4 different positioning satellites networks, has to have very good camera. These days now 4K video, both being able to take the video and then show the video. So all the very latest, all of that available on chips that we sell today. And those are now down to the 20 nanometer size, the latest ones. Now 14 nanometer and working on 10, and probably 7 may end up being about the end of that path for Moore's law, we'll see. But I'm sure there'll be some other ways to go. And even now, because of power and heat issues, rather than having, say, 1 CPU on a chip, go to 4, and now 8 CPUs, each one running a little slower, but among the all of them having a lot more computing power. And so we've come a long way since thinking about having CDMA. Some people saying it's too complicated, to now being able to handle all these tremendous capabilities on chip. And that's, of course, now led to many other possible uses of these devices we're carrying with us, the cell phone. And I know there's a lot of activity here on biosensors, that the whole medical profession is going to be transformed by both new sensors, new ways of monitoring, being able to communicate them, having a lot of computing power very close to you. So these signals are often very noisy, very low signal noise, but enough computing power to get the signal out of the noise and then communicate to you, to family, to doctors, information that might be needed. And so I think probably many of you have little wristbands or watches now that provide some of this information, but clearly the sensors that are coming along are making them more and more sensitive, and it's turning out to be already quite effective. And in fact, I believe you're moving toward a medical school here with a lot of engineering in the medical school to really make a lot of this move forward that much more rapidly. So that's an area of great interest. You've also probably heard of the Internet of Things. That is, now we're about 7.2, 7.3 billion cellular connections. That with the Internet of Things, that number is going to go up. What does that mean? It means that most devices will probably have an inexpensive capability of communicating through the Internet to other devices, that they will be providing sensing information of various kinds. We know that there's a lot of activity already in the automotive industry toward providing smart electronics on the cars. Certainly computer-assisted driving, many perhaps autonomous under certain circumstances as we go forward. This building's been designed with great concern for energy efficiency, and so the sensors will be both at the energy generating side, but also in the transmission side and the usage side. So in helping to keep down the use of energy, we'll be seeing a lot of wireless parts. For example, I'm sure most of you read on digital books. Shortly we'll have interactive digital textbooks becoming quite widespread. But again, that's somewhat of a machine. You order a book on for your phone or device from Amazon. Actually, that is going through the cellular network to your device, and it's all machine-to-machine communication once you select which book that you want. In fact, for the first year plus of Amazon, all that information was going through the network operating station that we had built for the OmniTrack system. We're coming to San Diego, we ship it up to Seattle, come back down and go back out again until they get all their software in place. So lots of activity in that direction going forward. Other areas, as you get more and more computing power, the so-called augmented reality approach, where you have something that is added to a physical scene that you're looking at. I think we're all used to it in football. But now there are device apps becoming available that allow you to do others, so you can hold your phone up and look at a sign and have it immediately translate into something at least that you can pronounce and understand what it might be. The one that's my favorite, given my age, is that you come into a room, there's some people there, a little camera on your eyeglass that kind of looks out for you and then whispers in your ear the name of that person, and then a little bit of information about the last activities you might have had. So helps that social situation quite a bit. And of course, all that technology is getting pretty close to being usable. So that's, I think, one that's going to be welcomed by many of us as we continue to age. Okay, what's been happening? These devices, of course, are getting so useful. Nobody wants to leave the home without them. And by the way, there are a lot of other applications, financial and otherwise, education. Mobile is by far the largest technology platform ever. Today, about 7.4 billion connections. There's only 7.1 or 0.2 billion people in the world, so already there's obviously multiple. And if you look at the growth, today, the second generation is still the one that's most dominant, but third generation is coming up, and behind that, fourth generation. These transitions take time to work their way through the system when you have these kind of numbers, but it opens up all kinds of possibilities. And the bottom one is for low power type systems that you might use for Internet of Things type of communications. And so the numbers are getting quite extraordinary. A couple of billion smartphones being sold basically in a year's time. The possibility, therefore, of coming up with new capabilities for the devices and, of course, for the software, and having a huge market, open market available out there for them. Spectrum, unfortunately, is limited, and so we often talk about the challenge of how do you get that much more data accommodated in a fixed amount of spectrum, relatively fixed. You can go up in frequency bands as we begin to do it now. And there are approaches for doing that that are part of what's now being referred to as the fifth generation, perhaps, new network approaches that involve many small cells, either in your home or out in the street. Actually, in New York City, we're putting them in old telephone booths now, that provide a limited range coverage, but that gives you frequency reuse and therefore more efficient use of the spectrum. Also, as you go to higher data rates, if you don't have to send the bits as far, you can get by with much less transmitted power and save also on the battery life. And so there's a whole range of new capabilities being explored to take advantage of these. There's also, as far as the basic technology, most of your cellular today is one-to-one. That is, a cell phone getting a stream of packets and sending back a stream of packets. Another approach, which is just coming into use now, is where you have multicast, where the packets, if it's, for example, a sporting event or a broadcast, a news event everybody wants to watch, you can send that string to multiple receivers and therefore get much more efficient use of the spectrum. So LTE-B for broadcast. Another approach, there's a lot of spectrum that's still available, and we use it for Wi-Fi that's unlicensed. It turns out LTE is actually a more efficient way of using spectrum, and so LTE-U unlicensed, and there's a lot of discussion about how that and whether that will go ahead, but a way to get more spectrum available, and particularly at the higher frequencies where we're going to want shorter distance, for example, sending 4K video from your phone over to your large screen 4K device, being able to move ahead. And also, right now, most of your cellular goes to a base station through switching or whatever, and then back out to your device from a base station. Well, you can go direct device to device and peer-to-peer type communications. So that's another step moving ahead to reduce some of the stress on the spectrum. So even though you might think that we're already seeing just about all the innovation and evolution, with this kind of demand and usage, it's really just getting going. Let me finish up with just pointing out with this number of users around the world, and in certainly developed countries, but in underdeveloped countries, the number of cell phone usage is going up dramatically, that there are a lot of very positive uses for the way people live their lives that can be made use with wireless devices. And so a number of years ago, we set up something we call Wireless Reach. We, Qualcomm, set up Wireless Reach. And we now have about over 100 projects in roughly 40 countries where we try to find a local partner to work with to try a different approach that could help people's lives and demonstrate it, and then hopefully it would go commercial. One of the early ones had to do with what we call Village Phone. Provide a box with a phone, a battery, a tower to put the antenna on, marketing materials, and an agreement with a carrier to share the revenue that might come in with that person. And for a few years, that worked out very well. It was mostly women that would buy the boxes, pay it off in about 6 months, and have a significant increment to income. That business is pretty well disappearing now. Why? Because everybody's buying their own cell phone. And so a number of the women said, hey, you know, this is great. We like being entrepreneurs. What else can we do? And so there's a whole set of different apps that are being provided. One of the more interesting ones has to do, of course, with money transfer. There are generally in undeveloped countries very few banks. And so how do you get money from one point to another, pay for purchases, et cetera? More and more that's being done by use of the cell phone. In fact, I'd say financial transactions are well ahead in Africa of where they might be at this point in the US. We'll see if that changes now with some of the new approaches, including the iPhone. And so that program is still ongoing and spreading. One that's obvious are help for farmers or fishermen. This one refers to fishermen, clearly providing information about the environment, the storm that might be coming, but even more importantly for fishermen, which fish are biting where, and finally, even more important than that, what can they expect to get if they sold those fish at different ports to different markets. And so that kind of information can be very useful, helps eliminate the middlemen. This has turned into, in now many locations, commercial business. One interesting aspect, most of the people involved, fishermen and the farmers before them, were illiterate. They had very little opportunity or reason to become literate. But now they're finding that indeed they can get a strong financial advantage if rather than just getting the audio and some pictures, they can get a lot more data by increasing their level of literacy. So it's having an interesting aspect in that way. Clearly, medicine is, as we mentioned earlier, getting impacted. One of the first uses was setting up clinics with various types of information that could be gathered, sent wirelessly back to a hospital, that information coming back, and being then used by somebody that really wasn't a doctor or particularly skilled. And so those programs have been in many, many countries now. And they're getting a bit more refined. For example, the cameras on the phones, of course, are very good these days. If you have a skin problem, you can take a picture, have that sent off, get it analyzed by a dermatologist at a location, information sent back about how that might be treated. And again, helping, we started that program first in Egypt. It's probably gotten slowed down a bit because of the political situation now. Another one that was interesting, I was back in 2000 on a tour having to do with the digital divide with President Clinton. And we stopped at a small town in North Carolina and set up what was then an experimental third generation system, a system that gave you access to the internet, and showed for a small manufacturing company there, an environmental manufacturing company, how it could benefit their business. And by the way, you can see President Clinton took him about an extra half an hour to ever get him away from the terminal. I didn't think they let him near one at the White House. Governor Hunt came up after the demonstration and said, look, you know, this is an experiment. We can see it's valuable. You have to promise to come back when it's commercial and provide some advantages here in North Carolina. So we said we'd do that. And so we set up one of the early classroom situations where we provided smartphones, and this was about 5 years ago or so, so they weren't as good as today's smartphones, to students in 4 different high schools. We arranged with a couple of universities to provide some material to augment the curricula. We provide some training for the teachers and provided aid as requested. At the end of the first year, it was actually caught us by surprise. There was one teacher in one of the high schools, very good teacher, but she had a class with phones and a class without phones. The class with the phones, 100% of the kids passed their statewide Algebra 1 exam. Without the phones, only 2/3 passed. And you expect a little bit of improvement when you do an educational experiment because everybody gets a little excited, but that was rather dramatic. And so the question, what were we doing right? And it turned out what was the best aspect of that was that they had these phones 24/7, that if you went home, tried to solve a problem, can't solve the problem, ask a parent, parent can't help. In the past, they'd have to wait till the next day. Now they simply go online, get help from another student, and be able to continue with their homework. And then students that came up with good ideas would send those around to the rest of the classmates. And so it was a lot of peer-to-peer education going on. And it turned out that this key item was the 24/7 and peer-to-peer type of education as being very, very important. And so we've continued to follow up on that. And finally, just one last project here. I know there's a lot of work on ultrasound. In fact, I guess the use of ultrasound for medical uses perhaps originated here. But one of the things we've done is have very simple devices that can be allowed to provide information during pregnancy, provide that to the phone. The phone then does its processing, provides information to the person, and if necessary, says perhaps it's time to go to a clinic. And so that is already beginning to have some very interesting results. And so one of the things we continue to do is, given all these devices around, given the possibilities of apps, given the computing power in the phones, all the other capabilities, continue to look for interesting ways of making use and really changing people's lives. Thank you very much.
Just want to thank Dr. Jacobs again for being here, presenting to us, showing us the history of wireless technologies, where it was and where it's going. So at this point, we have an open reception prepared for you all, that'll be after a Q&A session. I just realized, we have to do a Q&A session. So if you guys had any questions, we set up a mic over here and a mic over there, kind of like how we do in 200. We can just, form a line up to the mic if you want to ask Dr. Jacobs a question, and we could probably dedicate like the next 10 minutes or so to that. If there are any interests or questions. Oh yeah, good. You guys can just stand up, start making a line whenever you have a question come to mind.
I have a question. How do you deal with overseas manufacturers?
How do we deal with overseas manufacturers? We try to work very closely with them. Qualcomm's business model, since that time when we did actually manufacture phones and infrastructure, we sold those businesses, and so we focus on the chips and software, and we work with helping manufacturers around the world be able to provide phones. So they do the rest of the phones, sell them under their names. We provide a lot of the software capability. We now provide designs for how to build those phones. And so we're very active with manufacturers just about everywhere in the world that want to build wireless devices. That, of course, helps because they have a lot of their own ideas. They therefore might be suggesting new capabilities that in their region would help them sell those phones. And so we listen to those and then put additional capabilities in the chips and in the software we provide with the chips to support that. It turns out then sometimes to be politically very advantageous. For example, in China, it took about 10 years to get CDMA into China for a variety of reasons. But during that, and then it took a while for them to go to from the second generation to the third generation because they wanted to have a home-developed, claimed home-developed technology. But we were able to have a lot of business there despite that by working with individual manufacturers who could then use the chips and software that have been proven internationally and export product. And so that tends to be the approach that we try to follow. What you might call a horizontal business model where you're enabling many manufacturers as opposed to vertical. Nokia used to be, now Apple, for example, very vertical, where you try to do most of the things yourself, although still use a Qualcomm modem.
So my question is, has Qualcomm ever considered or will it consider moving from being a fabless company to becoming an integrated device manufacturer?
Yeah, Qualcomm's a fabless company in the sense that we do all the design, we arrange for all the testings ourselves, market selling, providing advice to other manufacturers, but we don't have our own foundry, so we're fabless. And fabs these days, as you begin to get into 14 nm, are costing multiple billions of dollars. So if you can have a company whose business model is to provide the fab, you provide the designs and go out and sell them, that works because you don't need to make that investment. Other companies, Intel in particular, for example, has been vertical in the sense of designing some of their chips, having foundries, et cetera. That obviously has some of its own advantages. We think the advantage actually works out very well with the fabless model. We've looked at occasionally, since we use not just one fab these days, but multiple fabs. Should we be investing in fabs? Should we be helping? But so far, we've decided that the best bet really is to work with some people specialized in the fabs. We'll specialize on the chips and how you make best use and sell them. Yes.
Hello, Dr. Jacobs. It's been a pleasure to hear your story. It's very inspiring. And you mentioned that when you started up with Qualcomm or even the first startup, you did not have a solid business plan. But did you have a plan B in case things didn't turn out the way you wanted to? And secondly, how important is it for someone in the industry working to have a plan B when they're starting up?
Well, I think probably you can say we had plan B, C, and D. We didn't have any particular product in mind when we started, and we just had the confidence level that we'd probably be able to come up with some ideas by talking among ourselves, talking with potential customers, et cetera, and hopefully a spark would fly, and then we could run with that fly. Linkabit, actually, the first company, we had a bit easier time in the following way. At that time, if you had a very clever idea, you could give it to a government agency, DARPA, or one of the other agencies, NASA or military agency, and within a very short time, get back a yay or nay. And often, if it's a good idea, you get back a contract with progress funding, and so that could allow you to move ahead. When we started Linkabit, when we started Qualcomm, we thought, well, we'd probably do the same thing, namely the first 10 years of Linkabit, 9 years or so were mostly government. Maybe Qualcomm would be the same, but the world had changed. And so at this point, you submit something to the government agency and wait and wait and wait, and then finally you might get back a response. So it's nowhere near as convenient a way to do the business, get a startup, as it was back in the Linkabit days. On the other hand, you're moving ahead. There are, I mentioned a small group before, some people define an entrepreneur as being somebody who's willing to fail once, maybe fail twice, and keep going. My own feeling is that it's important not to fail, that you do need to have ways of moving. If the initial direction isn't quite working, why is it not working? What can we do? Be prepared to modify your approach and try to find a way to make it successful. And if you kind of think about that, you can think of that as a plan B. If it's a distinct change or a kind of slight redirection, I call it dynamic programming in a sense as a business model. But it turns out to be, I think, a very good way to go. And so in most of the things we've been doing, we have come up with the idea. It's always taken some adjustment. It always takes twice as long as you originally expect when you come up to actually get it to market, at least twice as long. And so you have to be prepared for all those alternatives. And then, as was noted with that Wall Street Journal, whenever you're trying to do something that's a bit original, that may step on somebody else's foot, they're always going to come up with complaints and why it's not going to work and try to dissuade you from doing it. And so as you think these through, you need to build up that level of confidence, say, you know, we're on the right kind of path. We need to stay with it, make this modification or that modification perhaps, but keep pressing ahead. And then hopefully things work out. Yes?
Regarding the projects that you mentioned in underdeveloped nations, how do you make sure that they're sustainable? Do you have certain measurables for them?
That?
In underdeveloped countries with the...
Underdeveloped countries, again, the main thing is to actually go out and talk with people that have been working in country and try to understand what might be something that would be useful, that could work out quite well. The cell phone idea was one of those where you sell time on the cell phone. And we've done that earlier actually in India before that became developed, et cetera. Now most people are getting the cell phone, so then the question is, what's the best thing for them to do? And often they'll come back with an idea, and you then need to help them with the software and the app to make that idea work out. One, for example, that we didn't think of as far as I know, but that did come back to us was, in some sense, the job market. And of course, that's happening in the US quite a bit now. But you have a resource, a capability. Somebody might need that. They want a small job done somewhere. And so with the cell phones, you can kind of advertise the availability of a capability or the need for one and get a match being made. And so we're seeing that ends up being a source of business. But all of these are often situations where you don't predict yourself. You provide some capability, and then somehow somebody says, hey, I've got an idea how best to use that. You might then help them make it happen.
So in some of your later slides, you talked about what you can do with smaller cell sort of setups and frequency reuse. Going forward, how do you see the role of like spectrum sharing and like that ideal cognitive radio sort of idea developing in the role of managing spectrum?
Well, in all cases of using spectrum, and particularly spectrum that may have other uses in that, you need to understand how that spectrum is being used and then adjust your use of that spectrum. And so most of this 5th generation, I think, is going to include ways of identifying the users out there, whether you should connect to them or not connect to them, what technology to use to avoid interference, etc., a whole range of possibilities. And then within the device have the capability of generating the and listening to the appropriate signal. So a lot of flexibility in the implementation as well as the sensing of the world around you. As we touched on earlier, by the way, this whole area of sensing is going to become more and more important with people walking around with these devices just about everywhere, getting some sensing of how what the environment is where they might be, feeding that back, being able to make use of that is important. And part of that use will be to understand how best to organize the network. And so all these things are coming together, trying to understand them. People also refer to a 6th sense or a 7th sense, that you are trying to understand your environment, understand it well with a variety of sensors, and then make best use of it. So everything is going to be adaptive. Yes?
Just one very quick question. Which kind of smartphone do you have, and why do you like it?
Right now I'm carrying a Samsung phone. I change my phones frequently because we work with many different manufacturers. And I was just actually over in China and on a bus with Tim Cook, and I pulled out my Samsung phone, and I got a little bit of verbal abuse. So, and that even happens with operators as well. That you, right now I have an AT&T phone, but we work with Verizon, with Sprint, you know. So there's always the issue of trying to cover your bases so you don't get a good customer upset at you. But the number of different devices coming out, of course, are quite interesting. We didn't actually make we have a venture capital arm ourselves, and look for small companies that might be exciting, etc. And one of them is Xiaomi, which is a phone manufacturer in China. And so we've been working with them early on. And again, you just find new ideas out there, and then some of them you can either try to solve yourself or work with someone else that's providing the solution. So all kinds of interesting things happening.
Good evening, Dr. Jacobs. Could you comment on the recent announcement of one of the major players, Samsung, dropping out from the list of the users of the Snapdragon chip?
We've never said which large manufacturer is not using the Snapdragon chip and is using their own chip, so I can't give a specific name. And we've been working with Samsung that you mentioned many, many years, and in some cases they have their own design capability and their own foundries. They make chips for us, by the way, and they make chips for themselves. And so they've often had some of their own and some of ours. We try to make sure, give them the incentive to have most of their own. I think that with any manufacturer, it ends up being a dynamic situation. I'm sure we're going to continue to do a lot of business with that unnamed manufacturer going forward, and that some of the rumors that are out there actually aren't accurate. There's been some discussions of chips, of that particular chip, overheating. In fact, it runs cooler than the previous generation chip while doing a lot more for you. We think we have, and I really didn't touch on it perhaps enough, but some great advantages. The decision we made early on was to try to integrate as many functions as possible onto that piece of silicon, because you're getting more transistors and it can do more and more capability. And so that was the approach we took. Others said that was the wrong approach, that you should have individual chips for capabilities. And that has a cost to it, but they thought it would give flexibility. So TI used to, for example, argue that we were following the wrong path on that particular area. They no longer are in the business. So I think actually the integrated approach is, we currently have a lot more integration on chip than anybody else. And so over time, people may try different approaches. I think a significant part of that will continue to be part of Qualcomm. Just before I left as CEO, I kind of gave a challenge to everyone. 3G was beginning to grow and become significant, et cetera. We were still a growing player in the market. There were other very large players. I said we needed to set a target of roughly 50% for our share of the market. And it was tough, but we're above that. And so we want to try to stay above that. Yes?
Hi. Thank you for the wonderful talk. I wonder if you can comment a little bit about China's recent $1 billion fine against Qualcomm's monopoly in China. And also, I wonder if you...
One question at a time, because my memory is not good.
Sure, okay.
Sorry.
Thank you.
China passed an anti-monopoly law several years ago, and it wasn't, it still isn't quite clear exactly what is permitted, what isn't. But they have been investigating. They investigated Qualcomm for a year. We were never allowed to talk about what that investigation entailed. They've never really been publicly very specific about it. But they finally decided that we would pay almost $1 billion fine, percent of some revenue in China, which is a not negligible amount of money, as you know. And also put some constraints on, in a sense, the amount of the price of a phone that we could then be charging royalties on. And so it had its downside, obviously, and also had some upsides, actually. It has given us some opportunities to clarify the situation with a number of other manufacturers in China on all of the various technologies. There was some concern. In China, the third form of CDMA was called TDS CDMA. China delayed going to the third generation for a year and a half or so, tried to get that working well, never did work very well. Went on then to, the only company that was required to use it was China Mobile. China Mobile then went on to press ahead to fourth generation as quickly as possible to go with TD LTE. And they are now the largest user of that. We were worried that we might get into a spat over whether or not that was going to be claimed to be a Chinese technology, but in fact, that was clarified in this whole area. And so there's always, whenever you do any kind of contract, any kind of negotiation, with governments you usually have a lot less leverage than with another company that you might be negotiating with. But there's you always have to find something that can work well on both sides and then hopefully get that agreed to. And so I think we're comfortable moving ahead.
I wonder if I can ask another code-related question. Like, I wonder if you know about Peter Thiel's theory about monopoly and innovation, and will the Qualcomm's monopoly actually stimulate or hinder the future mobile chip innovation? You know, the Qualcomm currently is the largest world provider of the chip technology.
I'm sorry. Yeah, my hearing's not too good. I missed. Did you guys?
Yeah, the monopoly and the innovation. Will the monopoly help stimulate the innovation or hinder the future innovation of the, yeah.
Well, that's always the issue when you, and again, it gets into the patent rights. If you innovate and you're very successful and everybody else was going in a different direction, so that gives you a chance to get into a lead, then you end up with a significant part of the market. And as a result, people can say you're being monopolistic, even though that you're competing on a very level playing field. And so if that is taken, that you just look at the market share and say, therefore you have a monopoly, you can end up, and that you're using it unfairly, that by itself, if people follow it blindly, can suppress innovation. And so I think you want to just keep things very innovative. The patent situation, again, being examined here, one gets into standards, and I may be getting a bit too much complication here, but when you write a standard, there are certain areas you've come up with a great idea to make that standard work well. They incorporate the great idea. Therefore, that's called a patent standard piece, something that you have some control over. And then there's an issue of, since people have to use your technology, are they being unfairly treated? And so again, that's something that's looked at very carefully. I myself think that when you have a very large business, you've been successful, there are always going to be legal challenges, there are always going to be intellectual property challenges. These kind of things will just continue on, and you'll have to kind of deal with them. We had a 3 or 4 year investigation on the monopoly charge by the European Union. They never did bring a charge and eventually dropped it. It cost an awful lot of money to provide the legal and documentary information. But these things just happen, and it's almost a part of doing business these days.
Thank you.
Illinois.